Good afternoon, this is Schweitzer, and we're going to do a little discussion here about a probable, let's say, lab question. So, you're in lab, you're given an acid, you could know I guess you could know the name of the acid or not, it doesn't really matter, HX, and you're told to somehow figure out what is the concentration of the acid, what would be the Ka of the acid, and what is the percent ionization of the acid. You're also provided in this particular lab with a solution of 0.5 molar NaOH, and of course we're looking at a titration tube. I'll just draw this out here and below here. We have a pH meter also that we're going to use to track the pH. So, a couple of things here. We want to be able to determine the concentration of the acid. Alright, so let's answer that question first. Concentration is equal to moles per liter. So right away, I like to use this table. Known, unknown, molarity, moles, and liters. The known is 0.1, the moles I don't know, and the volume I'm going to add in a certain volume of this 0.1 molar NaOH, and I don't know the volume of this. You could start up a start and change table, but you will find that in this particular situation we will not need this. The unknown concentration is what I want to find. These are equal. The volume of the unknown, so somewhere here, let's say you take 10 milliliters. Okay, this would be equivalent to 0.010 liters. Okay, so at this point what we're going to do, and I might not give all the answers here, I'm just going to walk through the ideas of how we might do this. We'll track the pH, and you'll see the computer, the pH meter, will read a little chart like this. It will say pH on the Y, and it'll say milliliters of base added. And because it's acidic, it starts out measuring pH. It's a weak acid, so it's probably like right around 3 to 4-ish. And then what we're going to do, we'll start a little data table here. The computer automatically does this for us, and we will just have the milliliters and then the pH, and it'll start tracking it for us. Likely we would add a milliliter and tell the computer to keep the pH. And then we just keep adding base, and it would continue to say keep the pH, and then all of a sudden, it would hold steady for a while. And I'm adding in a little bit of this and saying to the computer, okay, record the pH. Or I could easily do this in Excel and manually type in a little table, the quantity of I added, and then the amount of pH that is associated with it. So you add them in, stir it a little bit, measure the pH. Eventually the graph starts to look like this. You notice that before, 1 small milliliter caused almost no change in pH. That is due to the fact that it's buffering at this point between the weak acid, HX, plus H2O yields X negative plus H3O plus. We have some of each of this. We have some initial amount of this, stoichiometric ratio, and I have some of this. Initially, I have all of this, and then eventually, as I neutralize, I am kicking over to this stuff, and I have some of each. As long as I have some of each of these, I am considered a buffer, and I will hold my pH relatively constant. But eventually, we run out of HX, because all of it gets moved over to here, and we spike through an equivalence point, looking something like maybe like this. And at this point, let's say this is a pH of 7 right here. You know, the equivalency point was in the, let's say, 9-ish range. So At this point, all I have is X negative. Here, all I had was HX. This is a weak base, so this must have been a weak acid. Okay, back to the question at hand. You take your equivalence point, drop it down. This gives you your milliliters of base at the equivalency point. This goes right here. Now you have the milliliters. Solve for moles using molarity equals moles per liter. And you solve for the moles because they're equal. Divide by the new volume, and you get your unknown concentration. And everyone's happy. Should be aware that, you know, the amount here, I mean, you might be able to do some proportional math. If you took 10 milliliters down here, 10 milliliters, and it took 10 milliliters just to get to equivalency point, so this is 10, then you know that they're the same volume, so they must have the same moles, which is the same concentration. So there's some proportional math that you should be aware of. Okay, now what about the Ka value? I'm going to just start this a little lower here. We start out, okay, you should be aware that we start out right at the beginning of our titration with just a beaker full of HX. And without doing anything, not the neutralization, just leaving it sit there, this thing is undergoing this chemical reaction. HX plus H2O yields X negative plus H3O plus. You don't have to do anything. You know, kick it, start it, scratch it, whatever. It just does it all the time. At this point, there's always going to be a balance between how much of the HX is present combined with how much X negative and actual H3O pluses are present. This is described by the Ka equals the concentration of the X negative, concentration of the H3O plus, and the concentration of HX. Hopefully, you note that very often we use, if you have the Ka, we might use a Ka along with an initial concentration minus X plus X plus X. This would look like the Ka equals my initial concentration. I'm just going to use it as a box here. Okay, and then X, and we get X squared. Given the Ka and the initial concentration, I'm going to call it a smiley face, okay, that I would be able to figure out how much actual concentration of X there is. This could therefore be converted to the pH, which is a pretty standard type of problem. We're going backwards here. We're saying, okay, we know the pH, what's the Ka? So this can be done at any point in time you want. It can be done right at the start. It could be done at the 1/2 equivalency point. It could be done at the equivalency point. Any time along the way, and this is where kids, it causes, no doubt, it causes kids some issues in this problem. So I'm going to do it just at the beginning. Okay? So at the beginning, now again, we would need to know our concentration to start over with. So what I want to do is, okay, I have HX, this is right here, plus H2O yields H3O plus X negative. Initial stoichiometric ratio, and if I know my initial concentration, so on my chart, I am looking at it right here. Okay? Now mind you, I just hit the 0 button on here and it gave me the correlating pH right at that point. So I know the pH at that point. So what I do is I take my initial concentration, okay, which is called a smiley face. I need to know that, which I calculated already in this video. not playing a role, minus x, 0, 0, plus x, smiley face initial concentration, minus x, x, and x. Of course, like I said, at this point, we have the pH right here. At that point. Why is there? And it's going to be acidic. So the pH is going to be acidic. Why is it acidic? Because this process is occurring. Not very much, but it's occurring. We're getting some X negatives. We're getting some H3O pluses. So the pH, what I would do is take the pH, 10 to the negative pH, and this is going to give me the concentration of H3O pluses, which happens to, because I was 0 and 0, happens to be that this essentially would be X. And X is going to be small because it doesn't get many of these products. Notice my picture here. I don't even have any H plus and X negatives. They are there, but they are in small quantities. So, again, to get my Ka value, all I got to do is take all of these values and plug them in here. This can be done at any point along the way. At any point in time, let's say I take 5 milliliters in, okay? So let's say, what's the Ka? Now the Ka does not change. K is constant, okay? For a given temperature. So let's say, what's the Ka? But I'm going to use the data at 5 milliliters to give me what I want. Okay, so again, Hx plus H2O yields X negative plus H3O plus. Initial stoichiometric ratio end. Now it gets more difficult in the middle, but it is still the same. Okay, what I would do is go to my data, and that's okay at whatever happened to be at 5 milliliters. What is my correlating pH? Okay, so now what I would do for this thing is I'd say, okay, well, I got two-step problem. I want to figure out all of these pieces. Water's not playing a role. This guy right here, and this guy right here. Okay, now, the pH, of course I know. I can convert this to concentration of H plus ions, and that goes right here. But I don't know the concentration, initial concentration of this, because originally some of it's gone. I have been doing a neutralization reaction. For 5 milliliters worth of my base, I have been undergoing Hx plus OH negative yields X negative plus H2O. I've been causing some of my acid to flip over to this. So my original acid is now smaller, and I picked up a little bit of this, which is fine. Okay, so now I have some HXs here. But I also have some X negatives. I'm going to go a few more HXs because I still have not at my equivalency point. But at this point I have some H pluses and some also X negatives. I'm still acidic because I have lots of H pluses, HXs yet. Just happen to have some of these. I cannot do this problem unless I know the initial concentration of HX and the initial concentration of X negative. So to do this, we do a little bit of stoichiometry. If you knew the amount of, I do this in moles, okay? If you knew the amount of HX you start with, and of course you know the amount of hydroxide you added, every one of these guys causes 1 HX to get kicked over. Now 5 milliliters of 0.1 molar NaOH, a quick math, would be 0.1 equals X over 0.005 is 0.0005 moles of hydroxide was added. Now this is a fictional problem, but this would be 0.0005. I would lose 0.0005 and I would gain 0.0005, assuming I had none of this to begin with, and whatever I happen to have, I would lose 0.0005 of it. And then I'd have my new moles at the end. This would be 0.0005. Take my new moles and divide by the new volume. Divide by the new volume in liters. And you get your new molarity. Now, at this point, once again, you plug your new concentrations in here. This guy goes there, and this guy goes right here. Minus x plus x plus x. And you get, I'm going to call it, I'm going to refer to this guy as a frowny face because he lost some. And this guy is going to be smiley face because he gained some. That's what the number represents. So this is now frowny face, and this is now smiley face. I got the frowny face minus x, and my smiley face plus x. Of course, the x gets dropped out as part of a shortcut rule. And of course, I have this value. So then, once again, this thing goes to equilibrium. It is these values will get shuffled into the Ka equals the concentration of my smiley face, which is going to be x negative, concentration of my H plus, which is the pH, divided by the concentration of Hx, which I had listed as the frowny face. So in this case, once again, if I know my initial concentrations, I can run my table through to figure out my concentrations at equilibrium and therefore calculate Ka. Some of the easier places to calculate the Ka value might be at the 1/2 equivalency point and the equivalency point. At the equivalency point, all of my Hx has just been converted over to x negative. So at that point, once again, I would need to use the x negative equation in order to run this math. Initial stoichiometric ratio end. Now I only have this concentration. I would go to my table and find out the pH at the equivalency point. So I'd be able to figure out the pOH from the pH. And again, this would be 0, 0, not playing a role, minus x plus x plus x. Missing piece, minus x, x, and x. Of course, this missing x can be gathered from the pH. That's another way to do it. So on my little chart, looking like this, it's really convenient to pick out the Ka here or here. And it's not that much harder at the equivalency, the half equals point, because at that point you can use either this equation or you can use this equation. Okay, and you need to figure out your initial concentrations based on some stoichiometry, but they are going to be equal at the half equivalency point. So that sometimes makes it a little bit more straightforward as well. They essentially, in the Ka expression, the concentration of my x negative will equal the concentration of my Hx, and therefore they will cancel, and Ka equals my x value, which happens to be gathered from the pH. So the negative log of your concentration at that point, I should say, my bad here, would be the 10 to the negative pH, gives you your concentration at that point. Alright, so either way, you would mathematically convert the pH to concentration, which equals x, and that will equal the Ka value at that point. So the half equivalence point is quite convenient. The beginning and the end are also important pieces. The last thing they ask us for, which at this point should be relatively easy to figure out, is what is the percent ionization. Now, unlike the Ka, the percent ionization does not remain constant throughout the titration. So we know that we have lots of Hx's here, and we have very few getting smaller here. And I'm going to draw this chart a little bit better, just so let's go like that, just for the sake of it. Lots of Hx's here, and right here we have none, just x negative. So as we move along this chart, the percent ionization is changing. So when I want the percent ionization, I'm really referring to what is the initial, right at the beginning, what's the percent ionization. And right away it's okay, well, H X plus H2O yields H3O plus X negative. And initial stoichiometric ratio end, I'm looking for the percent ionization. Okay, so I need to know my initial concentration. That is going to go right here, times 100. I need to know how much is changing here. Sometimes a delta sign is used this. That essentially is minus X, not playing a role, plus X, this unknown value minus X, X, and X. Of course, you should note that on your table, at this 0 added, right at the beginning, you have an associated pH here. This pH that gets converted to H plus ions, and that is my X value. And that goes right here as well, which is the change of your original amount, how much changed by this equilibrium reaction. Divide it out, times 100 gives you percent ionization. So this lab, although is our generally sometimes thought of, and it's just a general introduction to acid base, it's got a lot of stuff in it and a lot of things you might want to be able to do. Thank you.